So the next speaker is Carles Blanch from Institut Curie. Collective migration of anisotropic cells organized by integer topological defects.
So first of all, I would like to thank Jean-Francois and Thomas for putting together this nice conference. And so today I would like to talk about a mode of collective cell migration that has to do with anisotropic cells and is mediated by integer topological defects. Okay, so in this talk, I will try to connect two concepts that are a priori unrelated. The one on the left is an example of a topological defect you see in a spiral, which is a concept of liquid crystal physics. And the one on the right is tissue morphogenesis, and I choose the regeneration of the hydra as an example, which is a biological, in this case, morphogenesis is a biological concept that has to do with the emergence of shapes in biological systems. So I would like to start by briefly introducing liquid crystal. So these are materials that exhibit intermediate phases between the solid and the liquid. And these intermediate phases are called liquid crystal phases, and they are characterized by the existence of long-range order, here represented in this slide by the fact that the molecules are oriented vertically. So the cells that we use in this work are myoblast cells. They eventually will form or will become parts of a muscle. And when you look at these cells as they migrate on a surface, there are two noticeable things. The first one is that their shape is rather anisotropic. And the second one is that the migration of these cells is mainly restricted along the axis defined by its body. So at this stage, we ask ourselves whether collectivity of these cells would form a long-range order as well. And now when you put many of these cells on a pattern, on a substrate, on a uniform substrate, and you let them divide, so division is these little spots that you see in the movie. As they divide, density increases, and the effects of cell-cell interactions also increases. And at some point in the movie, you will start to see the emergence of multicellular domains that share locally the same orientation. For example, this domain here, this domain there, and this is what we would call long-range order. So if there is order, there is disorder. Another prominent feature of liquid crystals is topological defects. These are well-known concepts since the 60s, and here I'm showing you 4 examples of these defects. The main difference between them is how the molecules, or the director field, represented by these lines here, organizes around the defect center. And in the 2 examples on the top, the director field rotates by pi when you do a 2-pi rotation around the center, and in the 2 cases in the bottom, the director field rotates by 2 pi, leading to their definition. So these are half-integer, we call it half-integer topological defects, and these 2 are integer topological defects. So next we wondered whether these defects would be also present in myoblast monolayers, and this is a mapping between these 2 states. And I hope you can see the analogy between these configurations. So the 2 examples on the top were extracted from the previous movie. I just take the best images, and the 2 examples in the bottom, I will explain in a few minutes how we obtain them. So the topic of topological defects in collective cell migration has raised recent interest because of a series of observations that find spatiotemporal correlations between topological defects and biological functions. And these functions go from cell extrusion, changes of cell density, or emergence of shapes, and in a variety of biological systems like in vitro cell monolayers, suspensions of bacteria, or more complex organisms like hydra. So what these evidences suggest is that there is a connection between order and collective cell migration that is mediated by activity. But in many of these examples, this connection is not clear whether it is mechanistic or not. And nowadays, on another side, so there is a development, or there is tools that allow us to explore the mechanical link between these 2 entities. And here I'm showing you 2 examples. The one on the top is with magnetic fields. and the one on the bottom is using the topography of the substrate. And by using these two strategies, you can induce ordered configurations on different cell monolayers that present topological defects that you would rarely see by self-organization processes. So there is a third strategy. Well, there is more, but this is another strategy by which we can control order in biological systems, and is inspired by liquid crystal physics, and is through confinement. And the idea is the following. So imagine that you have a confinement that is very large. So the effect of the boundaries is very minimal. And what you expect is that the cells in the center would form essentially the patterns that they would form in the absence of confinement. So this is similar to the previous movie, with domains of ordered cells and topological defects in between. This is the +1/2 and the -1/2. But as you decrease the confinement, you gain order from left to right. And this is represented by two facts. The first one is that the number of defects decreases. The second is that their spatial organization also becomes more ordered. So this work essentially started with the following question. What happens if we now take this system and we confine it further? Is there a configuration where we can effectively fuse these two +1/2 effects into an integer defect? And when with the experiments, what we find is this state, which is not anymore similar to the previous states. And what you can notice is that the cells at the interface, they are well ordered. And the cells in the center, they are highly frustrated and very disorganized, because they want to align with the neighbors, but the effect of confinement is so strong that they are highly frustrated and they form this kind of disorganized arrangements. So I would like to stress that the experiments that I will show you from now on were performed by Pau Guillemat, who was a former postdoc in early Lab. And what Pau found in this state is, in this system, is that essentially there's three different dynamical phases. You have to remind that in this system there is cell division, so cell density increases from left to right. And so at early times and low densities, the cells organize into this configuration that we call a spiral that exhibits collective rotation. And after a few days, they switch into another state where the cells align perpendicularly to the interface, and there is no more collective rotation. What he found is that after a few weeks, there is a new state that emerges in which multicellular structure grows in 3 dimensions from the base of the substrate upwards. And as you can see from this graph, the height of this structure is much larger than the typical size of the confinement, suggesting that the shape is rather cylindrical. So given this self-organization process, we wanted to understand more deeply how cells were able to give rise to these different dynamical states. And in particular, the question that we ask ourselves is how the interplay between activity and order mediated by these integer topological defects, under which condition it can give rise to these 3 different states. So in the rest of my talk, I would like to focus on 2 main questions. The first one has to do with the fact that at that stage, we knew very little things about the mechanics of these cell monolayers. So we wanted to use this setting to learn and estimate some of the material parameters of the cell monolayers, and I will explain how we obtain this. In the second question, I would like to use this information to make predictions on the latest stages of evolution of this system, and here I will focus on the collective migration in mounts. So for the first question, in this system we have effectively stabilized 2 topological defects, so a spiral and aster. The spiral, we can stabilize it by using mitomycin. And the idea of this approach is to use these topological defect configurations to probe the mechanics of the system and to infer the material parameters of the cell monolayers by studying the mechanics in these 2 configurations that in this system we had for free. So I want to stress that similar approaches has been used on passive liquid crystals, for example, in these works here. And what we did in this study is to extend these approaches to active liquid crystals. In order to study the mechanism, so we use a coarse-grained theoretical framework. It has been already presented several times throughout this conference. I would not go much into the details, but just to reiterate that the idea is that we don't aim to describe every detail inside of the cell, how the organelles move relative to each other, or how the actin cytoskeleton organize, but rather what we aim is to describe the dynamics of some averaged fields, like the average cell density, average cell velocity, or average cell polarization. And to construct the dynamical equations associated that will describe the dynamics of these fields, we use the active gel theory. And this theory, in the past 20 years, there is a whole range of examples where it has been used to quantitatively interpret biological systems under different conditions. I cannot name all of these examples, but I would like to stress that this theory has been also made predictions. And these are two examples that I know so far. One is the spontaneous flow transition by Raphael Bouturier, and the other is vortex lattices by Amit Tusmahamadi. And if you know other examples or you disagree with these ones, I would be happy to discuss. So, okay. So a bit of the details of the theory. So we use essentially an active liquid crystal description. For those of you who are familiar, so the equation of the stress, the first two terms corresponds to the viscous stresses, and the other terms in black is because of the liquid crystal nature of the material. And in relation to the activity, we consider that these cells can exert active forces through three different mechanisms. So essentially, they can exert isotropic forces on the environment by these active isotropic stresses, or they can do so anisotropically, meaning that they exert different forces along the direction of the particle orientation or perpendicular to it. And the last mechanism is cell crawling, that we also hear several examples where we assume that the cells are polarized and there is a traction force on the substrate that the cells can exert on the substrate. So the next equation is force balance, where the internal forces are balanced by the forces with the substrate. And the first term is viscous friction that Pierre Réchaud explained. And the second term is these crawling forces. So for the rest of the equations, we neglect the effects of cell division. We consider that the number of cells is conserved. And we take standard dynamics for the polarization field. I want to stress that in this description, we make an assumption that we think is specific for the system. And this is that we assume that the disordered phase is favored at equilibrium by taking psi positive. And we think that this is a feature that is only applicable for these very small confinements, because the size of the defect is comparable to the size of the confinement. Okay. So we start with this approach because it was shown that in a simplified limit, asters and spirals can be stable solutions, and they exhibit collective rotation. And I will not go much into the details of the analysis, but I want to highlight the philosophy of our approach. So here as I said, we have spirals, we have an aster, so we measure different mechanical quantities in these two configurations. In particular, we measure the orientation of the cells in the spiral configuration. We also measure the degree of order for three different confinement sizes. And we measure the azimuthal velocity in the spiral case. And for the asters, we quantify the cell number density and the forces in the system. The forces, it's a rare measurement in this type of studies. And here we were able to do it by placing pillars in the center of monolayers and looking at their deformation. And we see, for instance, that the cells exert compressive forces. So the idea is that we have these quantities. Now we can use the theory to feed the data and find what is the parameter space that best fits this data. And what we were able to find at the end of the day is we could identify single parameter space that could fit the previous experimental observations. In this parameter space, we could constrain some parameters and others were bounded. And this is not simple rheological study because, for example, we could get the viscosity, but in addition to viscosity, we could get also parameters related to the activity of the cells or parameters that control the dynamics of the orientation of the cells, like, for instance, the flow alignment parameter that this setting allows us to give a first estimate of it in biological systems. I would like to stress that if we remove order from this description, then we were not able to fit the data, showing that order is necessary to understand the mechanics in these two states. And so what we think is that this approach highlights that topological defects can be used to characterize active liquid crystals. So I already explained you about the mechanics in these two states. Now I would like to switch gears and describe the growth of these protrusions. So here I would focus for the next part of the talk in the protrusion state. What we call protrusions is this multicellular organization. Here you see labeled the nuclei. You have to imagine that the cell shape is anisotropic. So the cells form a nice 3D liquid crystal organization. And this, in addition to the statics, this organization is also dynamic. So as you can see in the movie on the left, the protrusions are not only able to grow in 3 dimensions, but they also exhibit collective rotation. So of course here there is many questions that we would like to understand from a physical perspective, but for today I would focus on one, which is how far can these structures grow? And the motivation for this question is that when we measure experimentally the height of these protrusions as a function of time, we see that when the cells are able to divide, the height is a growing function, and then there is no sign of saturation. So we wondered ourselves, okay, how far can these structures grow? Well, when would we reach saturation? Would it be in 2 days, in 2 weeks, in 2 months, in 2 years, and so on? So this is a question I would like to address in the next slides. And so to address this question, let me first give you another piece of evidence on this system. So here what you see in the image is the actin filaments fluorescently labeled. And this is a Z stack. So the first slide corresponds to the bottom of the mounts. They are relatively small mounts of about 30 microns. And as the movie plays, we will go from the bottom to the top. And what you can see in this movie is that the actin organization changes as you change, as you go towards the top. And in fact, when we do a quantification by analyzing the orientation of the filament in 3 dimensions, here I'm showing you the distribution of the in-plane angle with respect to the radial direction. You can see that this distribution shows a marked peak at about 0 degrees for low heights. And as the height increases, this peak shifts towards 90 degrees. So what this suggests is that essentially in the mouse we have an organization which corresponds to an aster in the bottom and a spiral in the top. So there is gradients of orientation also in the vertical direction. And so in the theory of active liquid crystals, it is well known that if there is gradients of orientation, when you couple them to activity, this can give rise to forces. And here I would like to illustrate this mechanism with this very simple example. So imagine that you have the 2 molecules oriented parallel to each other. In this case, there is no gradient of orientation. And each cell is exerting a force distribution like the one sketched by these arrows. So if the 2 cells are oriented in this configuration, the forces that the cells exert on each other, they exactly cancel and there is no active force. But the minute I introduce some distortion in this system, then these forces don't balance anymore, and then there is the emergence of an active force in the system. Okay? So this is effectively one of these local windows on the aster configuration. And now you can imagine that the force field here is computed through the theory. So for this particular case, we expect an inwards active force. The nice prediction about this mechanism is that if now we change the organization of the cells, we keep all the parameters the same, we only change how the cells they are locally organized, you get completely different active force distributions. And so what the theory would suggest is that the mechanics in the mounts is different between the base and the top based on this mechanism alone. And so if we go to the theory, and for instance, we compute the stress difference between the asters and the spirals, and here I'm neglecting anything that is in between, I'm simply serving a 2D monolayer, as a function of the angle of the spiral, you can see that the difference between these stresses increases when you increase the tilt of the spirals. In particular, what we expect is that there is, at the center of these mounts, there is an excess compression in the aster with respect to the spiral. And now you could imagine that this excess compression leads to cell extrusion, and this cell extrusion would move the cells vertically upwards. So this is a candidate for the driving mechanism for the growth of the protrusions. We know the amplitude of the active stresses for this mechanism. Now we need to think about what could be the stalling mechanism. And here there is many candidates. For this talk, I was very naive, and I simply consider that the stalling mechanism is gravity in dry mediums, for which we know an estimate of the effect of the forces because we know the density of cells and the gravity constant. So if we balance these two effects, we get a length scale which is about 10 centimeters. And what this tells us is that if the protrusions are smaller than 10 centimeters, you would expect the active stresses to drive the flow of cells vertically and drive the growth of the protrusions. But if it's larger than 10 centimeters, then gravity will dominate and will collapse the protrusions. So this is the limit length. So with this prediction in mind, we went back to experiments and we tried to push the system as far as we could to see what are the most extreme situations that, to see whether we could achieve something close to this limit. And so this is the most extreme protrusions we could achieve. This is a zoo of the different possibilities, so you can see it's highly heterogeneous. There is single protrusions, and there is also mergence of protrusions from different patterns. And for this talk, I would like to emphasize that if you take the length of one of these big protrusions, you get about 1 millimeter, which is still far from the theoretical threshold, but it's closer than before. So with this, I would like to end my talk by reminding you about this schematic and thanking the people who have participated, especially Pau Guillemat, Aurelian Roux, and Carsten Cruz, and also you for your attention. So thank you.